Hi, everyone. So today we don't have Matthias, so you have to do with me as your host. But anyway, we are very happy. So to have today Elena Caceres from University of Texas at Austin, who will tell us about sparse SYK models. So please, Elena, go ahead.
Okay, thank you very much for the invitation. And I think it's a great initiative. So I hope you guys keep on doing this. It's really a wonderful way to have seminars available to everybody. And well, today I'm going to talk about sparse SYK models and some work that I did with my student Anderson Misobuchi that I'm doing right now with Anderson also and with another student, Amir Ras. This is something kind of new to me because usually my work all my life has been more kind of GR-ish. But last year I got interested in and I had never worked on SYK or anything like that. But last year I got interested in these sparse SYK models, and maybe for reasons that are not so usually you of course we know that the SYK models are like the only model, one of the only models that we have that is really, we think it has a gravity dual. And so in that sense, it's a wonderful thing to explore. It has been explored a lot, right? But then the sparse SYK models came up, and I got interested in them because they had an ingredient that is like the formalism about hypergraphs that I really appreciated. And so one of the things that I want to tell you about is this whole story about hypergraphs, and then how that was useful to get the results that we got. Okay, and also in learning about this sparse SYK, then I got really very interested in like the ability to these models give us to push as the numerical simulation of SYK and to reproduce and obtain black hole physics. So, okay. So I think that was my introduction. So just a reminder about the SYK that probably you all have seen before. Let me see if my pointer is working. Yeah. Okay, so we have n Majorana fermions, these guys with all-to-all random interactions. So this is a Q-body interaction. Usually it's taking Q equals to before, but we will see that Q equals 8 also has very interesting results, probably more interesting results, but it's more numerically demanding. These couplings are like random couplings taken from a Gaussian distribution. So in this sense, the SYK is really not one Hamiltonian, but a bunch of Hamiltonians, an ensemble of Hamiltonians. And so its properties are defined like the mean of these couplings is 0, and the variance is this Q minus 1 J. This is a parameter that sets the scale that has unities of energy, and that's defining the variance of the model. So we know that this is analytically solvable at infinite n, and we can make the connection to JT gravity and all that. We can see that there's an emergent conformal symmetry. It's maximally chaotic. All these things have been studied very thoroughly in the last years. But so the great thing of SYK is that it's a model of holography. We can see that it's amazingly a quantum model that has black hole physics. But it is very computationally expensive in the sense that we cannot, if we want to study numerically things with very large n, it's very difficult. Some people are very interested in SYK and the possibility of simulating SYK in a quantum computer. So there are many lines of work in that direction. For me, I'm not really interested in that. I just want to do numerical simulations in classical computers and things that you can compute, in any supercomputer that is available right now. But in any case, if a quantum simulation, the experts say that for Q equal 4, the number of gates goes like n7 to the 7 halves. So if you want large n and times time, so it's very expensive to do these large scale simulations. And classically, the number of terms scales like n to the q. So again, the state of the art, we can do n equals 52. This is 7 million terms, right? So it's a lot. So it's hard to see how we can push this more, like larger numeric simulations. So then the question came up some years ago, a couple of years ago, if there is an SYK modification that retains all the interest in physics, but is more computationally efficient. And that's how the sparse SYK came up to be. So this was work by Susskind, Brian Swingle, Shenlong Xu, and Su, I think, yeah. So the sparse SYK. So what is the sparse SYK? The sparse SYK really intuitively, it's a very simple model. You have your SYK model and you can think about randomly pruning. That's one of the ways of that you more intuitively can think about it. You can say, I'm going to randomly erase some of the couplings, set them to 0, and with certain probability. And you can imagine that if you erase a few, then nothing is going to happen. You will still have the same physics, right? But then you can keep on asking, so what's the smallest number of couplings that I can keep turn on and still retain the same physics? That's what the sparse SYK is. So there are different ways of introducing this sparseness. One of them is random pruning, and the other one is hypergraphs. I will be mostly focused on the hypergraph story because I think it has been, for practical computations, we use the hypergraph story, and the mathematical aspects of it has not been very much explored, I think. So anyway, the random pruning, though, is more intuitive to understand, because you can say, oh, okay, I have my SYK model that I just showed before. And then, but now I have this parameter here, xji to jk, that I'm going to set to 0 with probability 1 minus p, or set to 1 with probability p. So when p equals 1, I just recover the standard SYK model. And otherwise, with certain probability, I'm going to prune the couplings. Okay, good. So what are the advantages of doing this? So before, we had the computational cost for the SYK model was n to the 7 halves. And that was for the n to the 7 halves was for q equals 4. If you increase the q in the SYK model, the n increased. Here in the sparse SYK, for a quantum simulation, the number of gates go just like linearly with n. K is a parameter of order 1 that we're going to see in a second. And for classical simulations that are the ones that I am interested in, the number of terms goes just like kn. So instead of having millions of terms, as we did for, say, n equals 52, with a parameter of k equals 4, we only have hundreds of terms. Okay. So the computational efficiency of the sparse SYK is really great. I mean, it allows us to do many more things. It was also shown to have chaos by these guys, Brian Swingle and Susskind and stuff. And then they also could do, to some extent, the formulation for the ones of you that follow the SYK, the formulation of the path integral of G and sigma, some collective fields, which essentially then they tell us that there's a gravity formulation. Now, the question of what's the gravity dual of the sparse SYK is not like 100% under control, as much under control as in the case of the SYK. So these guys, Susskind, Swingle and stuff, they could show that there was some kind of JT gravity emerging, but there were also some other modes So it does have a gravity dual, but exactly what it is, it's not as clear as in the case of the SYK. But anyway, my approach is a little bit like from the other side. So I want to see the black physics emerging from the quantum model. So one thing that is not very much understood and is still being explored is how much sparsity can we have? So this K, I will show you in a second, is the one that like controls the sparseness of the model. As you can see, this K is the one that will tell me how many terms I will have at the end. And it's an open question. So how much sparseness can I have? And can we use the sparse SYK to see physics that we couldn't with the SYK because it was so computationally expensive? That's essentially the theme of the talk. Okay, so we're okay so far?
Okay. Can I ask you a question? Sorry.
Sure.
Is there any relation between K in this on this slide with P in previous slide?
Yes, with the probability. Yes, in a second we will see. Yeah.
Okay.
So yes, definitely K and P are related. Okay. Okay. Cool. So for this formulation, for the sparse SYK, as I said, you can think about it in terms of random pruning. But we're going to use the hypergraph formulation. This was completely new to me, this story about hypergraphs, and I find it really very interesting. So I want to spend a few minutes talking about this. So probably you are kind of familiar in some sense with the idea of a graph, and there's a whole branch of math that is called graph theory, and there are many results and stuff. So these objects called hypergraphs are a generalization of a graph where hyperedges can connect more than two vertices. In a graph, you have an edge connects just two vertices, right? In a hypergraph, you have an edge connecting many vertices. Now, when I was reading about this, it's a very powerful kind of formulation that is being used in many areas. I was surprised to know that it's used in areas as diverse as neuroscience to model like how signals can travel in the brain, to model how fake news travel in society. So because it has the potential of having like many things that connect each other at the same time, right? So, okay, so this is usually a graph. We denote it by G, and it's a set of vertices and edges. And this is the normal figure that we have, and an edge connecting two vertices. Okay, so a hypergraph that would be denoted by H is a set of vertices also and edges. But as I said, this would be now the hyperedge. Instead of the line, this would be a hyperedge, can connect more than two vertices. Okay, so the set E here of edges, right, is the set of pairs of vertices, while here is just the hyperedge can connect many vertices. It's a non-entropy subset of B. Okay, cool. So that's the idea. Now, when we deal with hypergraphs, we don't really, unlike with graphs that you can really draw a lot of like figures and diagrams, because you can think about three graphs and you can think about different types of structures of graphs, and it's very easy to like picture them. Hypergraphs really, you don't go around drawing these type of things. It's more, you think about them in terms of set theory. So all the mathematical results are in terms of people have proven many different theorems like sets, right? This is just a set of vertices and a set of edges that can contain any number. Okay. So there are two two properties of the hypergraphs that we're going to be interested in. So hypergraphs is a big topic, but we're going to be interested in some particular type of hypergraphs. Because our hypergraphs, if you think about our Hamiltonian, we have this term, right? This term that it's always connecting, let's say 4 or 8 of the Majorana fermions, right? So these hypergraphs always have to have like these 4 or 8 vertices. Each Majorana fermion is going to be like a vertex, and my term in each Hamiltonian is going to be like a hyperedge, right? So those type of hypergraphs are called uniform. It's when every hyperedge contains S vertices. So like here, all of them, all these hyperedges contain 3 vertices, right? So let's say for an SYK that has Q equal 4, we will be interested in hypergraphs that are 4 uniform, right? That I always have this, always contain 4 vertices. There's another type of hypergraphs that's called regular. Are regular when all the vertices are containing R hyperedges. So each vertex is containing, say, some certain number of hyperedges. Okay. So these are the type of hypergraphs that are going to be of interest for us, the ones that are regular and uniform, R regular and S uniform. The R regularity is, the fact that it's uniform, as I said, it just comes from the structure of our Hamiltonian, that we always want to have terms that have 4 Majorana. We don't want to have terms that have 4 Majorana and 8 Majoranas and different numbers, right? So they have to be uniform. Every hyperedge contains certain numbers of vertices. The regularity is an additional constraint that is imposed. Okay, cool. So we want regular and uniform hypergraphs. Cool. Specifically, we want the sparse SYK is realized as KQ, this K parameter, KQ regular, Q uniform hypergraphs, right? The Majoranas are identified with vertices, and each interaction term corresponds to a hyperedge containing Q vertices, Q uniform. Each vertex is containing KQ hyperedges. Q uniform indicates that the Hamiltonian contains Q body interaction. This is essentially what I said before. Okay, so here's the question about the relation of P and K. So K quantifies the degrees or the degree of sparsity in the Hamiltonian. So it's just K's P divided by N times the N choose Q, right? So in this, the sparse the SYK Hamiltonian has, it corresponds to the case when P equals 1, okay? So if P equals 1, the number of terms in the Hamiltonian is always Kn. When we recover the sparse, the normal SYK when P equals 1. Okay. Good. But for our sparse SYK, really this P is going to be a very small number. But what we essentially rephrase the whole thing. We're no longer talking about P anymore, because P is the random pruning formulation. When we talk about this hypergraph story, the parameter is K, but they are related. Okay. So now, so we want these objects that are called regular and uniform hypergraphs, right? But we want really them to be random, because our Hamiltonian is given with this random coupling. So it turns out that there are mathematical results for random regular and uniform hypergraphs. These are very recent results. So one of the things that surprised me when I also started learning this thing is that graph theory is a huge and very powerful branch of math, but hypergraphs, many of the results for hypergraphs, they are pretty new. Like some of the results we're going to use in the next couple of slides are from 2019, from math literature of 2019. Because not everything that has been proven for graph theory immediately extrapolates to hypergraphs. So, okay. So what we did is we went and looked for results in the literature for random RS regular hypergraphs, and what can we learn from that? One thing that I learned is that there's this object that contains a lot of information about the hypergraphs that's called the adjacency matrix. Okay, but anyway, before that, we want sparse hypergraphs, but we want them still to be highly connected, right? Because this connectivity is the one that is going to then produce all the physical properties that we have, and this highly connectivity makes it closer to the all-to-all SYK. There's a name for those hypergraphs. They are called expanders, okay? And in the math literature, there are ways of quantifying how good an expander a hypergraph is. So, for example, one of them is the spectral gap. Then the other one is called the algebraic entropy. And there's the other one called the vertex expansion. And there are more. So what I thought is, well, let's look into these measures of connectivity of these hypergraph expanders to try to get an idea of what is an optimal K. Remember that one of the questions is, what is the sparseness? How much sparseness can we have and still have black hole physics? So before going into doing numerical simulations and just trying, oh, let's try K equals 1, let's try K equals 2, let's try K equals 4, blah, blah, blah. Then I thought, well, maybe we can get some knowledge of what good Ks are, what is the optimal K, if we look at these measures of hypergraphs expanders. And it turned out really, it worked really well. So anyway, so all these measures that they go by different names, algebraic entropy and vertex expansion and all that, they are all related to this adjacency matrix, different properties of this adjacency matrix. So what matters here is, it's really the spectral gap. Anyways, the adjacency matrix is defined as this matrix that has an entry equal to 0 if I equals to j, or the number of hyperedges containing the I and j vertices. So you have two vertices and I and j, and you say, oh, how many hyperedges contain this pair of vertices? And that's the entry for your adjacency matrix here, or it's 0 if I equals to j. So this is a matrix that you can build. Given a hypergraph, you can build this matrix very easily. And then you can ask about the eigenvalues of this matrix. And that's what's called the spectral gap. The second largest eigenvalue of this matrix is called the spectral gap. And that guy, the spectral gap, the second largest eigenvalue, contains a lot of information about the connectivity of the graph. These are things the mathematicians have put in, not me, okay? So here, what do we have here? We have a plot of lambda divided by lambda max, right? So the spectral gap, the spectral gap is this lambda for different values of n and q. And this dot thing is the SYK measure for different n's. So we want this graph, so n equal 40, n equal 24, and n equal 40. Okay, so we want this plot to approach as much as possible the value of the SYK, right? And this is k. So from here, you can get already an indication for which k, like say k equal 1, it doesn't seem to be too good. K equal 2, it's better for the 8, for q equals 8, right? So, okay, so that's one measure, than the spectral gap. we can look at the other measures of connectivity. So these are all math results that they have many other results, like say for random walk, how long the times they're called covering times. So if you start in one of the vertices and have a propagation of a signal, how long does it take to cover the whole hypergraph? There are many results, but anyway, I'm just looking at connectivity right now. So the other one is called algebraic hypergraph entropy. And again, has a definition. This is all matrices. That is not, it's very simple to write the Python code of 5-6 lines and you have your matrix and all your eigenvalues and everything, okay? So the object here, again, is defined in terms of this adjacency matrix that has certain, the one that we saw before, but now the object that they define is some L of H that's defined that way. And then we look at the eigenvalues of this L of H, and we can define some kind of algebraic entropy using the eigenvalues of this L. So that's another measure of connectivity. And this is what happens with the algebraic entropy. So again, we have the dotted lines is the value for the SYK, and we would like to approach that value as much as we can. And we have plotted for different n's and different k's and different q's. And from here, again, you can get an idea of which k is good given a certain n and a certain q. Right. So that's my second measure, and there's another measure of vertex expansion. This one is a little bit more sophisticated. This is the one. These results are from 2019. It's essentially you have to define given a vertex, what is the neighborhood of that vertex. Okay. To some extent, like all the other vertices that this given vertex is connected to for some given edge. So you define the neighborhood, and then there's this guy is proved and a lower bound on the expansion. So the expansion is the size of the neighborhood divided by the size of the subset. Yes, that's what they call the expansion, vertex expansion. So this is a math result here. Again, RS here, I remember we define RS regular hypergraphs. So for us is KQ is R and S is equal to Q. And lambda is the spectral gap. So all these results, what you really need in order to quantify all the expansion of this graph is just this adjacency matrix and calculate the lambda. And then all the other things are like different mathematical results that rely on this spectral gap. So, okay, so this is the vertex expansion. So how much this neighborhood of each vertex, how big is the neighborhood of each vertex compared to the size of certain subset? And again, here we have the result for the SYK. And you have for different n's and different q's.
Sorry, Elena, super trivial question. K equals, what is the limit where you recover the original SYK? K equals to infinite, or you don't recover?
No, you recover, but you have to just it's a number that depends. It's a number that depends on n and q. So you put 1 here. And this is where you recover the SYK.
Yeah. So in these plots,
it's a number. It's a number you will have to do 1 over 24 times 24 choose q blah blah blah. Okay, but this for the SYK. They can be obtained analytically, because since we're defining our KQQ hypergraphs, you can just calculate those things analytically and you get, say, this result, the specific results analytically.
No, I was just asking because it looks like some measures don't asymptote to the SYK result. No, like in this.
Like which one?
Like for instance, the previous plot or the plot after this.
This one.
Yeah, like it looks.
Yeah.
Like
So this one, yeah, they kind of go to the SYK result. I wanted to point just kind of making connection to what you are saying. I wanted to point out that the Q equal 4. So the Q equal 4 in this case is the blue and the green, right?
Mhm.
In all the cases, you will see that the Q equals 4 is less of a good approximation than the Q equals 8. The Q equals 8 asymptotes much faster to the SYK result, right? And remember that these are measures from hypergraphs. Which one of these measures to what extent these measures actually contain physics, we'll have to see, right? We have to see calculating stuff for real physical results, right? So from here also, you can see that the Q equals 4 is the blue, the Q equals 8 is the red. So the Q equals 4 takes longer to asymptote to the SYK result than the Q equals 8, right? So this is just like intuitively, you can see that the Q equals 8, so your SYK with 8 Majoranas is much more connected. It's going to be much easier to get to the SYK result, right? So that's a feature in all of these. All of these, the ones that are worse, let's say, the ones that are worse are always Q equals 4. The Q equals 8, they asymptote much faster to the SYK result. Okay, but you can also, so from this thing, you can say, okay, this one say the Q equals 8. Remember, these are just hypergraphs, so these guys know nothing about physics. It's just the connection of the couplings. Okay, so far we don't know anything about physics. The next step is to say, aha. So from here, what can I say from here? I could say that for Q equals 4, I need to go to a higher K. I need kind of K equals 4 or more. And I could say that for Q equals 8, because that one is asymptoting faster to the SYK, maybe I can get away with K equal 2. That was our naive guess after we saw all these results, okay? And then we have to go and actually do physics calculations and see if this is, you know, meaningful, or use this as a guidance and see to what extent this is true. So here's where I'm going to show you now the results for the traversable wormhole and in the sparse SYK, and then another thing that we're doing right now, which kind of like tell us that the hypergraphs are giving some information, some interesting information. Anyway, oh wow, I talk a lot about hypergraphs. Okay, so we have 2 coupled sparse SYKs. Maldacena and Chi formulated the traversable wormhole in SYK itself, like the formulation of like eternal traversable wormholes. And they obtained the solution from JT gravity by adding coupling to the boundaries, and it's traversable. And you can derive the same physics by just considering 2 copies of SYK and adding an interaction, this interaction. Okay. So what we wanted to do is to see, we wanted to study this same thing in the sparse SYK and to see for what K, I mean, first, can we reproduce the traversability of the wormholes with this sparse SYK? And how does K affect this story? Okay. Well, so the main thing, well, we did a lot of things in the paper, but I'm just going to show you like a few things. First off, we will have to check that the ground state approximates the thermophile double for some temperature. We did that, so that's check. I'm not going to show that. Then a result that's pretty cool is the energy gap scaling. So this energy gap scaling was derived from large N analysis gravitationally by Maldacena and et al. So this is a result that comes from gravity, okay? And they found that at weak coupling, meaning small mu, right? This is the weak, when I say weak coupling now, I mean the coupling here. The this should scale like this power. So it's like a non-trivial power, 1/2 minus 2/k, this energy gap. And strong coupling, it should be linear with mu. Okay, so that is a result derived from gravity. And you can see in the SYK itself that it obeys that result. So the question now is, what happens with the sparse SYK, right? So these are numerics thanks to my student Anderson Mitsubishi. And this is the nice result. So this is Q equals 8, K equals 2. So just taking the indication of the K from the hypergraphs, we said, let's try with K equals 2. And what are we seeing here? Well, this is the linear scaling with mu. And this is the one that has the weird power. I think in this case it's 7/4 or something here. And you can see that this is really nice because it actually follows the prediction, the gravitational prediction very well. In this range, for say small mu's, it follows this weird scaling, this power, this some 4/3, 7/3, I don't remember what it's scaling. And then as you increase mu, it goes to the linear behavior. So yeah, so this is a result that I like a lot. And the thing is, did I put it here? Yes, I put it here. So remember we were saying K equals, we already agree that Q equals 4 was not, in the hypergraph measures, was not approaching all that much the SYK results, and it was not converging as fast and whatnot. So this is for Q equals 8, K equals 2. If we try to do the same thing for Q equals 4, K equals 4, so I mean even increasing the K, then we cannot reproduce the gravity results. So these things don't behave like, they don't follow this scaling. We would have to see some part here, but no, nothing goes there. Okay, so we didn't see that scaling, that gravity scaling for these values. Okay, so that's for the traversable thing. So Q equals 8 matches the scaling expected to gravity at large n, but finite n effects dominate the very small couplings, mu, blah, blah, blah. Okay. Now, there's another physics associated with this, which is called revival oscillations. So the idea is that you start with a ground state of the two coupled SYKs, and you create the Majorana excitation on the right. Then the excitation will get scrambled. And because this is a chaotic system, it will reassemble itself on the left of the system. And then this process will repeat. It will go back and forth, left and right. And this was called revival oscillations. Okay, this was a study by these guys. In the gravity picture, this means that the perturbation is traveling through the wormhole and then coming back and forth and back and forth. Okay, and in the gravity side, I think this was Maldacen and Chi in their eternal traversable wormhole paper, and the quantum system were these guys, revival oscillations. Okay, so do we have these oscillations in this sparse traversable wormhole? So the diagnostic of revival, you have to define a transmission amplitude, and then this T square is the probability of recovering this one on the other side after you insert it on one side, what's the probability you have it on the other side? Okay. So this is a picture from these guys. So this is for the SYK. And what do we see here is that the main indication, so let's see, this is if you didn't have them coupled, so just have one SYK. So you do your excitation and then it dies off with time. Now, the green and the orange is when you have left and right, okay? And what happens at the beginning, let's say you start with left, and it starts following very much the SYK, it decreases, decreases, decreases. But then all of a sudden, the green that started in 0, it has a spike in the green. And then they start oscillating. So that spike means that the green, that it had traversed to the other side, right? So the characteristic of these things is that when these oscillations, when say the left is in peak, the right is like at the bottom, and they just exchange like this, okay? So again, this is you start on one side, it starts decreasing, just following kind of the SYK, but all of a sudden the other probability picks up. And so this one completely decreases. And then after some time, this other one picks up, while this other one has decreased to 0, to very low value. And that's the revivals. So the question is, do we have this in the sparse SYK? And for what K, right? So here are our results for sparse SYK. Again, this is Q equals 8, K equals 2. And different values of the temperature. And this is the same idea, T left and T right. Now I have them in dashed and solid lines. So you see that we can see these oscillations, right? When one is up, the other one is down. We see these oscillations, and they are dying in time, but we see the oscillations. So this was pretty cool. I do not know if I have the plot. I don't have the plot of the other one. But if you try again, Q equals 4, K equals 4, we did not see the oscillations. So for Q equals 4 and K equals 4, we just see something that kind of decays, with very tiny wiggles, but nothing as clear as this. Okay. Cool. So far we're very happy. Here I said it. SYK with Q equals 4 does not follow the expected frequency of scaling on ADS to gravity, but Q equals 8 is here I would say sparse, of course. Sparse SYK. Okay. So our diagnosis so far has been that we did more things in the paper, the Green's functions and whatnot, but the things that I show you were the energy gap, which is pretty convincing, that follows the scaling with gravity, and these revival oscillations that we're able to reproduce for certain values of Q and K. Okay. So the summary so far is hypergraphs are a useful mathematical framework that provides information about the connectivity of the sparse model. Sparse SYKs, yeah. So all these numerics, except for the one of the energy gap, but the numerics in the paper and everything that has to do with time evolutions was done using a Python library that's called Dynamite, that is good for parallelization. And they were all done by my student Anderson in using the Texas Advanced Computing Center, so a supercomputer, whatever. But it's just, you know, a Python code that you parallelize massively. That's it. Okay. So this is all about trying to see if trying to check that the sparse model has the properties that it should, and like see the traversable wormhole and see things that were already discovered in the SYK, right? And see for what K can we see that. Okay, so now I want to show you something that people could not calculate in the SYK because it was too computationally expensive, but that you can do in the sparse model. And for that, we have to talk about chaos and the spectral form factor. So I'm running short of time. So I probably can skip this. Classical chaos, we have the sensitivity to initial condition, and quantum chaos can be diagnosed in many ways. One of those ways is the out-of-time order correlators. That's something I'm doing now. Well, the basic intuition is how much an early perturbation affects the later measurement. And you can deduce a Lyapunov exponent and all that. Anyway, this is something not for this talk. Another way is random matrix theory. And the idea, this idea due to Wigner, was that in a chaotic system, by studying statistical properties of random matrices, of course, subjected to centered symmetries, we can understand the statistical properties of the energy levels and eigenstates of the system. Okay. Not many of the observables that we compute in physics, they are not sensitive to these energy statistics. So there's this thing that people in condensed matter have been calculating for a while, the spectral form factor. This one calculates, even though physically it's not a very intuitive thing, like, you know, what exactly it is an observable that does capture the statistics of energy levels. Okay, level statistics. Random matrix theory provides it's an alternative way of diagnosing chaos. And yeah, quantum chaos is encoded in the statistical properties of the spectrum. The spectrum chaotic systems show the same fluctuations as predicted by random matrix theory. Okay. Okay, we know this. So I guess this is the main thing. If you define the level spacing as this difference of energy divided by the mean level spacing, this Wigner prediction of Wigner surmise is that for quantum system, this probability of finding consecutive eigenvalues at a distance s is going to follow something like, it's something like this. Okay, where these exponents here depend really, and these coefficients also depend on what type of matrix ensemble are you considering. Gaussian orthogonal, or Gaussian unitary, or Gaussian symplectic. These are all well known. Okay, so let's erase that. And if it's an integrable system, it would just follow a standard Poisson distribution, something like this. Okay, cool. So that's the level of statistics. And the quantity that is sensitive to this level of statistics is the spectral form factor, defined like this. This spectral form factor has a disconnected part and a connected part, right? Okay. And this is probably something that you have seen, that is a very famous result by a large group of people, including Schenker, Stanford, and Polchinski, and many other people, where they calculated the spectral form factor of the all-to-all SYK, and they show that in the late time behavior. So late time, here this plot, people refer to this part as the slope. This is the dip. This is the ramp, and this is the plateau. Okay. The big thing about this work that was super important is that they show that this behavior is really indeed is the behavior expected by random matrix theory. You can just do a random matrix calculation and you will find the famous ramp, this famous behavior. Okay, and this behavior of random matrix theory is supposed to be very universal. So this part of the plot is supposed to be very universal for almost any chaotic system, even gravitational systems, so black holes also, okay? This part of the plot, the slope and all that, it's not universal, it's more kind of dependent on the system, so it did not receive much attention. This whole thing, the whole thing is about, it was about this large time behavior of the spectral form factor. And this is when probably you have heard this story that here we have these two disconnected geometries, but later here we have the connected geometries, a new saddle that is the connected geometries like Euclidean wormholes dominating the path integral and all that. So there has been a lot of study about this. Okay. Now, in 2020, Berkus, Bruckner, Noravlansky, and Raz, they did an analysis of the expansion in higher moments, and they found that the expansion in higher moments can dominate at early times. So as I said, this is not the regime. This late times is what everybody was talking about. These guys focus on early times. So this is not, it's not meant to be a universal property as universal as random matrix theory, but they did an analysis for the SYK and expanded in contribution to higher moments and they showed that they could dominate at early times, the connected part. So normally the standard law is that all this is the disconnected part, okay? Well, but the thing is that you cannot simulate in order to see that effect, that these guys proposed, you had to go to a very large N, an N that is not available in the state-of-the-art numerical simulations for the all-to-all SYK. Okay, so you could not actually do numerical simulations and show that yes, they indeed dominate, the connected part dominates. But as we said, one of the advantages of the sparse SYK is that it's more accessible to numerical simulation. So then we thought, okay, so let's try to do it in sparse SYK and see if we can actually verify that effect of that the connected part contributes in early times. And so this is what should be out in next month or so. It's just a short note. And yeah, so we can see that indeed, these are the connected and disconnected part. So the connected is the blue one, the disconnected is the red one. And we can see that there's this point early in time, so much before the dip. So before what is always said is that it's here where the connected and disconnected parts, exchange dominance. But what we can see is that at large enough N for the sparse SYK, that exchange of dominance happens before. And here we have a plot of, we call it T critical as a function of the sparseness. So as your graph becomes more and more dense, you do approach more and more the value of the sparse of the all-to-all SYK. So you become more, this point comes lower and lower and lower here, okay? But the point is that the sparse SYK is the whole beauty of the sparse SYK is that it's a whole class of models that they themselves have gravity duals, right? So what is this? This is the whole spectrum form factor here, which I just plotted the connected and disconnected part. This is the whole spectral form factor, this one. And it's a little bit hidden behind this because at the beginning it follows this part, then you have it here and then it's hidden behind the orange, but that's essentially the same effect as before. And this is for k equal 4 and equal 30, q equal 4. And so you can see that there's this new effect that the connected part dominates earlier. Now, this is not the super cool Euclidean wormholes of this part, because the Euclidean wormholes is like a new saddle. So it's not the same as this. It is just expansions in higher moments, or as some people call it, like fluctuations, global fluctuations of the naive saddle, as it's called. Okay, so it's not the same as the effect at large time. What is the interpretation, the bulk interpretation of this phenomena? It's at the moment unclear. It's not known. These guys, the ones that conjecture the existence of this thing, they propose that, okay, so it's like we have two disconnected geometries, but somehow they are connecting and it's not a wormhole because it's not this other saddle that is at late time. So what could happen is that there are some light fields that are, somehow in the bulk that live in the whole geometry. So that's what they suggested. There's no much other than I mean, there's no calculation, there's no really proof of why in the bulk, why is that happening? But just from a simple quantum mechanical point of view, like from the quantum system, you can see it happening. Okay, so I'm kind of out of time. So then there is autox. What we are doing is calculating the autox in the sparse SYK. We hope to be able to like extract the Lyapunov exponent and all that. Let me finish with some future directions, which this is also something I'm interested in. Very recently, Heil and Shao came up with this story, this like question you can ask is, okay, we have a traversable wormhole, we can make a traversable wormhole, whatever we know, we connect these to that, we have a traversable wormhole. What is the observable that can diagnose when signals collide behind the horizon? What is the physics thing that I have to calculate to say that things collide behind the horizon? And so these guys proposed this 6-point function, this 6-point function. So it's like an autoc, but instead of being a 4-point function, is higher. And they show that this is the observable that you want to calculate if you want to say if things are colliding or not behind the horizon. And they have explicit scalings, diagnosing things and whatnot. So I would clearly like to try to do this in the sparse SYK. After we finish the autox, I will try to see this and then actually seeing in the quantum model like this signal, just like we saw the signal of the energy gap that follows so nicely the gravity prediction. I would like to see this thing calculated in the quantum model following the gravity prediction of these guys. Then there's a lot of stuff that goes back to my interest in hypergraphs, because another field of interest in this whole SYK, sparse SYK thing is operator growth or complexity. How as time evolves an operator gets more and more complex, or how it grows. And I think the hypergraphs would be a good language to address this type of things, because I said, as I mentioned, they have all these different measures of like covering times. How long does it take if you start with an excitation on one vertex to cover the whole hypergraph? And for me, intuitively, that has to be related somehow with our notions of operator growth, or how complex it gets. Anyway, and there are many other things that one can explore using this. First, this is a sparse model that is more amenable to computational calculations that are not so hard. And then this whole story about hypergraphs, I think it can be explored much more to our advantage. Okay, so that's it. That's all I have. Thank you.
Thanks, Elena. Thanks a lot. Very nice talk. Very clear. We have time for questions. Please, people, don't be shy. There will be time for shy people where I stop the record, but I will only do that after there are some questions.
Yeah, probably I can start. Hi, Elena.
Hi.
Hi. Yeah, I have a question concerning the scaling you showed with mu. There was this, if I got this right, this large mu regime where it scales like just 1/mu.
Which one? The scaling of what? Of the energy gap? This one maybe?
Yeah.
Yes, this one.
Yeah. Here, right, yeah. Where you say that. I mean, this works for this Q equals 8 model, but not for the Q time generator.
Yes, that's right.
So, but in gravity, it seems in the low mu regime, the scaling with this fractional power goes down, forever. Whereas in the sparse SYK model, it's just an intermediate regime where you get this fractional scaling, right?
Yes, that's right. That's right.
So
we're only able to see it in this for some range of mu's. We don't see it for arbitrarily small mu's. And it could be that finite n effects are dominating this part.
Okay. Yeah, so that was my question. What is, so to speak, the non-gravitational physics that breaks which makes this other regime? So my understanding is that if it would be full everything described by gravitational physics, then it would have this fractional scaling.
Yeah, it will have this fractional scaling, this fractional scaling for all small mu's, and then it will just transition to this. So this part is great, right? Yeah. This part is how it should be, but we don't see it continue it here. And it's probably just finite n effects, because we did this with, well, 2n = 40, 44 and stuff. So yeah.
Okay, thank you.
Sure.
Martin has a question.
Yeah, so thanks for this very nice talk. So I've got a question concerning the question whether these connected diagrams dominate or not in like for the spectral form factor. Mm-hmm. So you showed the results for the sparse SYK, but now my question is really, if you now push the sparse SYK to the all SYK models, whether the dominance really is gone or not. So can you do kind of an scaling analysis in your K to basically say something about whether you still have this dominance of the connected diagrams or not? Yeah,
so that's a good question. So first of all, the result by these guys, which is for SYK itself, for the all-to-all SYK itself, it was not a numerical result, right? It's an analytical result that lit a bunch of graphs, and it's very, very impressive work. And but you cannot see it numerically. Okay, so okay, fine. So what can we do? And what we did is what's it called? This the critical time where they exchange dominance here, right? Where they exchange dominance, we could see that, as I said, as you increase we pushed our numerics as much as we can to be like closer to the all-to-all SYK, and we could see it like lowering, becoming lower and lower and lower and lower. Okay, now what I think it's going to happen, what these guys said. So these guys argue that in the all-to-all SYK, in the honest to God n goes to infinity all-to-all SYK, there's still going to be a difference between the dip time and this time of exchange of dominance. But the difference between these two times is just going to be so small that you cannot resolve it unless you go to very large n. So that's the conjecture. So what I can tell you, what we did is we saw this time going down as we increased the sparseness and stuff. The conjecture is that what these guys say is that difference is going to survive, but it's going to be almost very close to this dip time. And that's why you cannot resolve it numerically. Did that answer your question?
Yes, so, but let me compare it to lattice gauge theory. So for example, lattice gauge theory is also very complicated to really do an honest continuum limit. So no one does. In fact, what they do is like a finite size scaling analysis based on a kind of an RG arguments. And so the question is, you have now certain results up to K equal to 8, at least that is what's shown in the inset. And now the question is, can you now guess how basically this TC, or is there kind of a scaling analysis, how it will change with K, so that you can use your numerical results for small numbers of K to extrapolate to larger values of k and to an all order SYK models?
Yeah, so an analytical scaling analysis. Yeah, no, we have not done it. I think it would be really hard. We have not done it. We did wonder about if this is what's going to happen with this thing, if this is going to continue growing linearly or going to flatten out. We do not know. No, we do not know. I mean, yeah, it's something we could look into, but yeah, we were just we wanted to see this exchange of dominance and all that, but there's definitely more to look into this. As I said, also the bulk understanding of what's going on, it's unclear, and that's also another question. But yeah, no, we did not do that scaling analysis.
Okay, thanks.
Thanks, Martin.
I have also a question, Daniel.
Yeah, go ahead.
Oh, maybe my question, Elena, thank you very much for the nice talk. Maybe my question is related to the previous one. In your plots, as we see, n is not too small. So my question is it possible to perform any perturbative computations in 1/n expansion in this sparse SYK model in order to, for example, partly answer to Martin's question?
Yeah, more than, I'm not sure if perturbative in 1/n. Yeah, that's probably a good possibility. Yeah, so essentially it would be like you could go here, you could go the paper of these guys, right? And then you could do, so their results, if you look at their results, so first of all, I mean, we had to make sure that their results will go through in the sparse SYK, right? So their whole results depend on a certain parameter, that they call epsilon, that it's n choose q times something, okay? And you can follow what they do. And then in our case, that parameter that governs this exchange of dominance and whatnot, now it involves the k. Okay, no surprise, but you can do that. Okay, now what you are suggesting, which is probably doable also following their methods, I'm not sure, I have not thought about it, is doing an 1/n expansion. I mean, yeah, maybe.
Thank you.
That's a good idea.
Okay.
Yeah, yeah. I mean, they are the ones that came up with this new effect, doing the. If you look at their paper, they have a whole thing about analyzing different type of graphs, and they call cactus graph and these graphs and all that. So I believe probably all that analysis can be done in a 1/n
expansion.
Yeah.
Okay, thanks.
Thanks, Nabil. We've had some questions, but okay, unless Elena has to go, if there are more questions, please go ahead. Don't be shy. If not, let's think.
Okay, can I ask one more question? Sorry.
Yeah, of course.
Okay, thanks. My next question, Elena, is after all these computations, can we say anything concrete about the specific value of k and q that we can use in our future computations?
Well,
in this?
Yeah, so I think depends who you ask. So if you ask me, I would say q equals 8 and k equals 2 is good, and the farther you can push q is better. So q equals 8 gives you better numerical results and whatnot, but q equals 8 is much harder to do numerically. That's why, I mean, we can do it with the sparse model, but if you look at the numerical results for the all-to-all SYK, they are 90% of them, they're with q equals 4, because when you increase the q, the numerics become really much larger, much more demanding. Okay, so if you ask me, I would say if you can do Q equals 8, that's probably going to give you better numerical results, stable and whatnot and all that. And for Q equals 8, you probably can get away with K equals 2. If you have to do Q equals 4, then you have to increase your K a little bit. So it would have to be K equals 4 or something like that. Now, the statement that you will see usually in the literature is very non-committal. So it's just say an K is an order 1 parameter, you know, like, yeah, it actually, as we see as we saw here, at least in this sparse model, Q equals 4 and low K will not give you the gravitational result, right?
What you showed us were mostly related to recent developments in gravity and SYK. Don't you think that transverse results should be that which is consistent with the very primary results of the SYK model? For example, it should give us the correct Lyapunov exponent. It should lead to some emergent conformal symmetry in the low energy.
So the emergent conformal symmetry has been shown already. It was in the original paper.
Okay.
That was shown. That it is chaotic. It's also, they had some arguments also that it was chaotic. Now the Lyapunov exponent has not been done, and that's what I want to do with my auto. So that's my work in progress right now with some other students. But yeah, it's a new model. I mean, if you think about it, this is sparse SYK. The first paper was in 2020, so it's not a long time ago. And that's why in the first paper, Saskin, Swingle, and other people, so they show the kind of the main features, like the formulation in terms of these G and sigma collective fields, and the fact that it's chaotic and the emergent conformal symmetry. But there was a ton of things to be explored and to be done, because yeah, it's a new model.
Okay, thanks, thank you.
Thanks, David. Any last question before I officially close the talk, and then just open the floor for any informal comment? Okay, I guess you made me happy. There was enough questions. So thank you very much, Elena, for a very nice talk.
Sure. Thank you for inviting me.
Very nice. And thanks everyone for attending. And let me remind you to stay tuned for next week. Same time, we will have Nico Joquera telling us about holographic QCD. So bye, everyone.